Now, what really happens if there are multiple obstacles? So I did it for the case where there was a Q robot over here and there was a point obstacle O. Now what if there is O1, O2, O3? Let's do it for that case, O4. Now there are two modelings. The first one which says F repulsion is equal to submission over all obstacles. So that's what you would normally do. You say that this is the this is an obstacle, so the repulsion force is here. This is the obstacle, the repulsion force is here. It's always opposite. This is the obstacle, the repulsion force is here, and this is the obstacle, so the repulsion force is here. You'll add it for all of them. So it's a summation. There's another modeling which says the repulsion force is the maximum due to any obstacle. So you say that in this situation, this is the nearest obstacle, so its force will be maximum. So F repulsion is equal to F repulsion due to O. Which one do you choose? Now, technically speaking, formally speaking, if you have situation like this, and if you take the max, the problem with max, as you know, is that the derivative will not be smooth. Suddenly the obstacle which you are considering for your repulsion, it changes, so the direction of the force suddenly changes, so the rate of change of force is not smooth. And because of that, if it was a vehicle, you would have got a jerk straight away, and that's exactly why it's important as well. The robot control algorithm will not be smooth. It will suddenly change the velocity direction, and suddenly changing the velocity direction, of course, no robot can do that. The limits will make sure that change is smoothed out, but sometimes you need to be careful that sudden changes in velocity are not even given to the robot. If a human is on a car, you will feel the difference. That's when you tell your driver, don't give such a jerk to me. And if it's a physical robot, it can sometimes damage it up as well. It's not good for it. And as well as if it's a robot, it acquires a lot of error when there's a sudden change. So sudden changes are not good. So it may appear that actually summation is better. There is no sudden change. But then we haven't looked at into practicalities. What we'll go and look at it soon. Now I've got an obstacle over here like this. So there are infinite point obstacles. Now do I really need to take this boundary, whichever format it is represented, and it's continuous, so integrate it over all O. Now that gives me the F repulsion. Most of the time, practically, this obstacle, its boundary is not known. I don't even know the boundary. So if I don't know the shape, how will I do this integral? And if I don't know that, what really happens is that I have ways, but which I'll talk about a little bit later. I find out which is the closest obstacle in this obstacle, so at the smallest distance. So I'm maximizing the force, repulsion, against an obstacle, so I'm minimizing the distance. Force is inversely proportional to distance. So I find out what's the closest point in this obstacle boundary. There are sensors which give you that directly. I'll talk about it later. And therefore, a sensor exists that gives me this, the obstacle, and I make F repulsion due to obstacle. So instead of integrating against all these points over here, I just took in all these points, the point which has the minimum distance to the robot, and used that to calculate my repulsion force. Easy enough. So here I am indirectly taking a max. It's max over forces by all these obstacles. And why? Because I don't have the surface boundary. In reality, however, there is a sensor which gives the shortest distance to an obstacle. And that is one of the popular ways to look at this problem. So if you have got multiple obstacles like this, not point. This is your robot Q. So in this obstacle, you take the one which has the max minimum distance over here, say O1. Here you take the minimum distance O1. Here you take the minimum distance O1. I won't consider these two. Why? Because they are outside my drep. And then you draw the free body diagram like this. So that is FO1. It's far away, so the force is small. This is more far away, so the force will be even smaller, FO3. And this one is, okay, that's also far away, so the force will be smaller. And of course, there will be an attraction towards the goal. And that is how your robot will move. So finally what I do say is both the modeling, so my F total is F attraction towards the goal plus summation of all obstacle, F repulsion from the obstacle, or you can take the max as well. And my robot moves in exactly the same direction. Now, after this, how do you really apply this force? I'm not going to speak about it. There are multiple schemes. And remember, this force is virtual. So don't put your hands up and say acceleration is force upon mass. I do not know the mass of the robot. It's constant. It's subsumed in the K attraction and K repulsion like any other constant. So there are three things which are popularly done, and what you do is what you experiment and find out is the best for you for the scenario. The first one, where what you do is you say this is your robot, this is the current orientation of the robot, which is theta, and this is, say, the direction of the force. So you say this is the angular error, and you say my angular speed is gonna be proportional to my angular error. So if the total force is here, I'll turn here. If the total force is here, I will turn here. Sometimes what you could say is, and let me do it for linear speed as well. So sometimes what you say, what the linear speed will be, so this force is the acceleration. So the new speed is the old speed, which is here, plus acceleration, which is over here in this direction, and some component of it. So that gives you a new velocity vector, and that is what you accept as the velocity term. Sometimes you say that the old velocity doesn't matter, it's a holonomic system, so it can turn in the direction of force anytime. So you say at any time, Vt will be proportional to F total t, which is as a vector. Sometimes you say that it's linear speed and angular speed, so you say that Vt will be V of t minus 1 plus projection of F total over the V vector. So let me take this vector as E, unit vector E. So it's up to you whether you model momentum or not, which is the part, the robot moving in its own direction, or you say that every time it just looks at the force and moves in the same direction, or you say that you will incorporate the kinematics or not. How you do it, it's completely up to your own. The only thing which matters over here is that there's a force that tells you what is the preferred direction of motion, and your controllers, whichever way you control your robot, though that's part of the control theory, not the simulation classes. As for the control theory, whichever way you need to make the robot control its linear and angular speed with respect to this force, you are free to do that. Now, what I will, of course, discuss is a little bit about the more complex scenarios. So this is where I am current. I mean, this is my office probably, and I am sitting here and delivering the lecture. This is my cabin, and outside my cabin, of course, there is a big hallway like this. This is what is the classroom, and it has benches kept like this. You cannot enter here, and this is probably the lab where I work. And if I am here and I am returning back to my office, this is the situation. Now, what we do is we divide this problem into a number of sub goals. So, first I need to go here, then I need to go here, then I need to go here, then I need to go here, and then I need to go here. And it's a natural environment. So, in natural environment, what happens is that there are known corridors. You are at every point of time at one or the other corridor, and all you're doing is either navigating at the first end of the corridor or at the second end of the corridor, and which end of the corridor you're navigating, it's known to you. And that's how we model the attraction forces: constant magnitude, direction at the end of the corridor. So now that's the end of the corridor. Now what will happen over here? Everybody will try to go to this end of the corridor. So magnitude constant, direction at the end of the corridor. I'll speak about this region in a minute. It's interesting. Now here it's a wide open area, so it's no longer a corridor. But then if you want to exit this building, then this is the door. You will have to travel through the door. So everybody wants to go towards the door. Now it's a constant magnitude and directed towards the door in open areas. So corridors, you always travel at the end of the corridor. Corridor, you always travel at the end of the corridor. Open areas, you travel at the end of the door. So similarly, this is a corridor. So that's the attraction force. So corridor, you always travel the end of the corridor. So you always travel the end of the corridor. So that's the attraction force. Okay, here probably I'll go in this direction. As I said that there are two ends of the corridor and application decides which of the two ends of the corridor. This is open area, so I'll go right at the center. That's where the door is. So I'll go right at the door. And similarly around over here. So that's an open area. I'll go right at the door. And here there's a specific goal. So here it becomes, so this conic constant magnitude directed at the end of the corridor, at the middle of the door where you have to go. Here it's quadratic, so it's directed at where I need to stop. That's what's the attractive force, modeling for normal office type of scenarios. Now, the little mess up here, how do you decide you need to go here or you need to go here? That is where the A-star algorithm comes into play. So, A-star algorithm says, travel this, this is a topological graph, just like your satellite navigation system, Google Maps, that's a topological graph. The equivalent topological graph of this thing is right around over here. That gives you the topology. And then you've got in this situation over here. So that's what is your topological graph. And then this is connected to here. And this goes all the way around over here. So you can do a graph search over this one. And once you do a graph search over this one, you will know that in which direction, which end of the corridor the forces need to be applied. And once you apply these forces, then you get straight away to the goal by these types of attraction forces. What is also interesting over here is how did I construct this topological graph? Topological graph of a place is constructed when the designer, in our cases probably the CPWD, the Central Public Works Department, in other cases whoever is the architect, gives you this thing. It's a line drawing, you can get it easily. So you apply the A-star algorithm over here and then switch the direction of the forces such that they go around over here. It only offers static obstacle avoidance. Of course, it doesn't offer dynamic obstacle avoidance, which is obstacle like this, which is where the repulsion forces will come into play. So attraction force will be here, but the repulsion force will be here. So the resultant force will be here as a result of repulsion due to this and attraction due to this general direction. And that's also very clear. We talked about rivers flowing. What is the potential? It's because of the slope. So, always in the direction of motion, rivers can go from mountains to oceans just by the direction of the slope. So, that's the attractive force. The repulsion force is when there are obstacles in case of rivers. Now, before we go on, let us look into just a few plots. And luckily I have them over here. Oops. So the first thing that we did was we modeled the quadratic potential, and this is what is the surface of the quadratic potential. This is the slope, and same example of a river. So that's how rivers will flow. Wherever you have drops of water, they'll go around over here. So if a drop of water is over here, it will follow in exactly this route and it'll go right till the sink. So the goal is basically a sink, and quadratic is a nice quadratic thing. And that's exactly what I said, that what will happen is that the forces will become zero right over here. So that's what you'll see, that the slope will keep on reducing and it will stop around over here. If I take a derivative, that's exactly what happens. So the forces are very large over here and the forces become zero over here. So if you take any random direction, this is the derivative of this. You start with large force, large force, large force, and look at the size of the arrow, they become so small, and here it becomes actually zero. So that is what is the quadratic potential. I haven't plotted the conic, but then it's absolutely very simple where all the directions will be constant. This is the repulsion, of course. So you can see these forces are very large at the obstacle, and here they actually die off a little bit slowly. At the obstacles, it's infinite. So you see 4 obstacles, 1, 2, 3, 4. The forces are infinite, and at any point it shows a nice curve like this, which is not visible around over here. So it decreases by the cube of the distance around over here. So as I go near, I feel a strong force outside it, and that's what you see. Very large force values pointing away from the obstacle, very large force values pointing away from the obstacle. So these are very large. Far, far away from the obstacles, nothing. And now, this is, unfortunately, these forces are so large that you cannot see most of the smaller arrows. So this is showing the direction of the arrows only. So here you see that this is very large, then it's actually pretty small over here, but then just to show where the arrow is, I plotted it by a large arrow rather than small arrow. So the size of the arrows is controlled over here. So wherever you go, you will go as far as from the obstacle as possible unless you reach this line, which is equidistant. At the equidistant distance line, you cannot go any further because whichever way you go, the obstacle will push you away. Here if I start, I'll travel here. Here if I start, I'll travel here. Here if I start, even this boundary is here, I'll travel here. So these are nice cartoons that help you visualize the forces. And if I happen to add both of them up, of course, that's what happens. You cannot see it because of the infinity. And therefore what I'll do is I cut this figure at this line, and this is what you see. So this is repulsion from obstacle, that's why you see this line over here, and it's attraction towards the goal, that's why you see this line over here. So anywhere if I start, I'll go, I'll get repelled, I'll get attracted, and I'll end up over here. If I start from here, I'll go down, I'll get repelled, and I'll go around over here. So just visualize the surface which generally has a sink at the goal and the obstacle shoo everything away. Any drop of water that you put, it goes away in the sink eventually. So eventually everything goes away towards the sink, and that's the only thing that I have to do. I need to make my robot go and get the sink, and therefore if I leave a robot over here, remember this was the goal, this was the sink, it travels over here, it gets repelled, and then it goes around over here. which is exactly same as I showed you over here. So that's where it started from. It get repelled, and then that happens over here. It happens to come over here. So that's a robot which is following this route.